Is this one on? Cool. Thank you guys so much for coming. This is awesome. So as you mentioned, this is an opportunity for us to build community around robotics, around applied AI ML, and hopefully around new emerging capabilities of foundation models. And so my name is Josh Rappaport, and I'm on the investment team at Innovation Endeavors. We're so excited to have you guys all here. I know some of you might be working into the wee hours of the night for your Coral paper deadline that's tomorrow, so I appreciate you guys making it happen. So yeah, Innovation Endeavors, we are a early stage VC broadly, and we were founded by Eric Schmidt about 15 years ago, along with Dror Berman. And since then, we made about 200 investments across a variety of categories. A lot of the work we do is in the intersection of the physical world and emerging technology. We also invest a lot in life sciences and some of the core underlying technologies around data infrastructure, dev tools, and security. But double clicking on the physical economy piece, because I think it's largely relevant to what we'll talk about today. Most of the work we do there has been around advanced data compute engineering as applied to traditional industries. So we invest a lot in construction, manufacturing, food and ag, climate broadly. And we also are very focused on technical teams. So a lot of applied AI ML and a lot of robotics. We've invested in probably a dozen robotics companies over the last decade plus. Companies like Vicarious Surgical, Gatic, Third Wave Automation, Canvas, Machina Labs, among others. So why are we here today? I think we're obviously in the midst of an incredible moment in AI, and I think the excitement around new capabilities of large language models and diffusion models and foundation models broadly is incredibly exciting. And what's happening in text generation, image generation, copy, design, art, it's really exciting. And I think that's captured most of the public attention. And so I think today we can talk about kind of what the next wave might be. And that next wave, I think, is just beginning to reach more of the public eye. And it's to do around how these new capabilities, along with 3D reconstruction, AR, VR, spatial computing, how those might impact the physical world. So some of the questions we'll discuss today, how can foundation models change robotics? How will neural radiance fields, NeRFs, allow us to simulate and model the world in new and exciting ways? What might an AI assistant for the physical world look like? These are just some of the domains we'll touch on. And so we have an amazing lineup of folks. Thank you guys so much for coming. So I'll turn it over to this group. We got leaders from Google, NVIDIA, Sail, and leading startups in the space. So I'll turn it over to Ryan Hickman from NVIDIA to kick us off.
All right, thank you. I am in my Miami Heat gear. I months ago agreed to come here, did not know that my Heat would make it to the finals. It is game 3 right now. It is close. I've been following the score. Johnny might remember 10 years ago, I did a mohawk when they made it to the finals. Not this year. Okay, are the slides in the same deck? All right. Actually, let me start my little timer so I don't ramble on too long here. There we go. All right, I am Ryan Hickman. I was at Google for about a decade. I've been at NVIDIA for a year, working on omniverse simulations and neural radiance fields that we're going to try to take out of research and bring to market. And that's what I'm going to talk to you about today. For a little bit of background, I worked on spatial computing. Had to start with this, given Apple's news this week with Johnny Lee, who's here. And we did put that on people's face back about 10 years ago, and that was fun. Worked on the Google Scanned Objects effort as part of cloud robotics. The whole goal was to scan objects so that we could train perception systems to recognize them for robots, but we got Google Shopping to fund it, and so you'll see a lot of e-commerce products is what we scanned 100,000 units of. Also put Android phones in a lot of places as a way to bridge robots and the cloud. So you could bring cloud services to robots, but a big part of it is knowing where they were, mapping, and so forth. In the middle, that's my son doing VR control of a robot. I don't think I was allowed to show the interface, so I blurred it out. And the bottom in the middle is some Unity renders of synthetic cats that helped Nest detect pets using simulation data. And now that I'm at NVIDIA, we use simulation a lot, and we have a lot of customers who are wanting synthetic data and simulation to train perception cameras, robots, wearables, self-driving cars, and using simulations is a great proven way to do that and to help you accelerate that development. But when you open your simulation tool and it looks like this, and you're a software engineer or an AI engineer, you don't know where to start. And when we come and tell you, you just need to hire a technical artist, an animator, a graphic designer, and a producer, and you're looking at a multi-million-dollar simulation content effort, it can be quite the turnoff. So what we really need is automated ways to capture reality. From whatever the sensors are, we need to automate turning those into 3D representations that you can work with and create your scenarios for your application. So one thing we can do is take insights from Google. Very few people have spent the money and time that Google has to create digital twins of the planet. They've been doing this for a very long time and just announced there on the left these new immersive maps, but they're taking two approaches. The one in white on the left is classical photogrammetry given to artists to make look nice in Unreal Engine. It's very visually appealing, but I wouldn't train an AI on it. The one on the right looks pretty darn good because that's using neural reconstruction from DSLR images inside of a restaurant that was reconstructed into 3D and remains very faithful to how the original scene looked. No, why is that not? Wah, wah. It was an animated GIF. Oh, is this like a privacy thing? Is it trying to protect us from hacking? Well, this was a beautiful animated GIF of a Nerf. We will move on. The way Nerfs work is a lot like photogrammetry, where on the left, you see all these input images. You got to estimate where those images came from in the scene, and you recreate a view. But the thing that made Nerfs magical was revealed recently by John Barron and his team who created that Nerf paper in 2020. And I loved this, where they said, hey, John, after you left, we tried adding positional encoding to the model. And look at the difference between the original plant and the new one. And his response was like, holy shit, I think that's the new Eureka. But it was slow. So 2 years later, in early 2022, NVIDIA came out with Instant NGP as a way to do 3D reconstruction really fast. So instead of taking hours to train a 3D model and then rendering it at 0.03 frames per second, which was excruciatingly slow, this ran fast. In Instant NGP, you can put yourself in VR and immerse yourself in a Nerf with stereo 60 frame per second rendering. And a lot of that is thanks to how the data structure is. The data structure uses this multi-resolution hash encoding. It's very cool, but it is not a standard. It's not like a 2D pixel array for a JPEG. If I send you a JPEG, you don't have to tell me what operating system you have. It's going to open it. But if I sent you a multi-resolution hash-coded file, good luck. So there are a lot of challenges with Nerfs, even beyond the fact that none of this stuff is cross-compatible. But the good news is, every day we wake up and new things are solved. As a PM, I love this because a problem of yesterday gets solved with tomorrow's paper. If I'm a researcher, I probably hate this because I'm getting scooped constantly. But the field is moving very, very fast. But at NVIDIA, we believe it's time for it to go to production. We think it's been 3 years since that Nerf paper, and we're seeing enough evidence that companies are adopting this technology in a lot of different engines that it's ready to come out of research labs and be something people use for production when you're designing your robots. Now, these fancy new neural assets are going to have to work alongside classical ones. So in here, we see a USD ADIC scene, which is a free sample. And we pan over to the cute little famous Lego dozer. If you've been following Nerfs, everyone always includes a little Easter egg with a Lego dozer. And that is not a mesh and texture of that Lego dozer in the scene. It's actually this neural radiance field that is being rendered alongside classical assets. And that means you can create these things without artists. You can just take pictures and boom, now you have a really good looking asset. And you can work with it in regular asset tools if we avoid fragmentation. So we currently have a problem in this field where there's a lot of innovation, but it's leading to fragmentation. So Valinga is a research lab spinout that will let you do this great nerfing, and you can drag this .nvol file into Unreal Engine. Cool. Luma Labs has a .luma file that you can drag into Unreal Engine. Cool. They're not the same, and they won't work in any other engine you try them in. So this is not good. So what we think we should do is not invent something new, but actually use something that's been tried and true. Has anyone in here heard of VDB or OpenVDB? No hands. So we have no one who used to work at Pixar or DreamWorks or visual effects studios. This is common, and this is actually a problem. a lot of really awesome things have been solved in the graphics field if you're doing fire and water and smoke for a film. You use VDBs. It was open source by DreamWorks a decade ago. It's awesome. But if you're in computer vision and robotics, you probably never heard of it. It's actually really fantastic. So what we think we can do is, instead of putting smoke and water and fire in these 3D representations, we should add neural information, neural features in the little voxels, so that we can infer them and get these fancy radiance fields back out. Here's a little demo of some early work on this. This was a 3-mile run around the Laguna Seca racetrack that one car ran around with cameras and LiDAR, and we reconstructed it in, I forget what it was. It was seconds. It took seconds to reconstruct this across a few GPUs, because this stuff's graphics accelerated. It's got a decade of investment in these VDB structures. And what these assets will have is they'll have geometry, they'll have radiance fields, they'll have your semantics. We can put a lot of information into these things. So that's a very quick run through. If you don't work in simulations or graphics, thank you for tolerating that tour of things that you may not care about. But the ability here would be to match what you do. If you're a gazebo developer, if you develop robots and you use Gazebo and ROS, and you're making LiDAR maps, you run the robot around your facility, you hit record and you save a ROS bag, and then you open that up in Gazebo, and now you've got a map and you can do regression tests and simulations, and you didn't have to have any technical artists. It's awesome. So when you start wanting to add computer vision, now you need that photorealistic version of that map. You know, there's been this gap that has not been able to be crossed yet. And so we think nerfs are the way, where in the future, very soon, hopefully months, not years, you'll drive the robot around your facility and you'll get a photorealistic digital twin that now you can train perception systems, train your planner, do a lot of other cool things with. So that's it for me. And I think, who is next?
And we'll have lunchtime at the end for Q&A. So you can just hold on to your questions, that we can look forward to that.
And you put me right after Ryan with the NVIDIA one. So I'm kind of the opposite. My background and focus is very much on the applied side. My name is Travis Dial. I'm the founder and CEO of Cobalt Robotics. And specifically, we do robots for safety and security applications. And yeah, we'll jump right in. So by way of background, I'm a technologist by background. Did my PhD at Georgia Tech doing healthcare robots. Ended up doing medical devices for a decade or so, and got sucked back into robots from an old friend telling me about this application in security. And so again, it's very, very applied for what we do, but it's really, how do we deploy robots into the world and leverage these amazing things that come down the pipe every other day from NVIDIA, Google, and others to deliver valuable applications, and very specifically around dealing with labor shortages. So security guards, we actually tie into camera systems pretty extensively, and we'll talk about that. But basically, how do we integrate robots into our daily lives? And so about 7 years ago, we started developing these robots. They're roughly human height, that would move around spaces much like this office building and provide after-hours safety and security coverage. So a single physical robot moving around the space, looking for anomalies, doing routine patrols, automatically responding to alarms. And the way we did that was through remote human beings who could be in many different places at once by way of this robot. So the robots are going around autonomously, pulling in people when they're needed. And then of course, there's wonderful data and analytics that a security director has probably never, ever seen before. So that was our early view of the world, was here's this robot, it's a very narrow application, put robots in lieu of guards. It turns out that's not the actual problem that you solve. The bigger problem, and you'll see this with many of the applications of robots today, is it's actually about a much more expansive ecosystem and fundamentally changing operations. And so for us, that's really around security operations. And this is lots of other devices, right? It's things from cameras and access control, even physical on-site guards, those remote operators, and then the new category of device, which is these mobile robots. And so, you know, we provide services that utilize all of these things. They're processing cameras, tying them to automatically dispatch the robot, to go check on things, building novel 3D models of the space, and being able to provide that long-term analytics of, you know, what went on. And so, yeah, again, we do all of it. We are a full-service security solution that happens to use these robots when and where it makes sense. From the technical side, we use a lot of the technologies that you'll probably hear about today. Obviously, we're a giant scaled up Roomba operating in commercial indoor spaces. So you can imagine that like, it's actually very easy to get a system up and going doing the basic task. It's all of these long tail things that you never expect to encounter, like random drunk people or crazy ramps and cords and just all sorts of ridiculous things that you encounter day to day. We are blessed in that we have a human in the loop that we can fall back to. And this is also great because we can use that remote operator to enable completely new applications. And so as an example, all the way back in 2020, we did like kind of the simplest thing you can imagine to ride elevators, literally putting a Dalek like poker on it and going up and poking the elevator buttons, which sounds ridiculous and simple and actually is ridiculous and simple. But now you have a robot that can ride up and down multi-floor anywhere in the building. And so it's a hugely compelling capability that doesn't rely on wireless integration, which we've also done pretty extensively. And so, you know, dealing with the practical realities of wireless connectivity in elevators, making these things available eventually, hopefully, to other robot platforms so that we can just do useful things in human spaces. Lots of interesting things that it turns out that the perception technology stack is just one tiny facet of how you actually deploy production hardware around the world. That's a hard problem that others in the audience can certainly tell you about. But you know, one of our core developments is really around, we have human beings as part of our core service. That will never go away in all likelihood. People are very good at having interactions with other people. And it has a big cultural element, but it's great from a robotics perspective because it means we don't have to have 100% fidelity on our solution. We just have to know when to call for help and to allow people to do that, you know, with latency from all the way around the other side of the world. And so at Cobalt, we actually run command centers that are staffed 24/7 in Utah, in Irvine, California, and in Manila in the Philippines. There are people right now that are monitoring and responding to security events all over the world, which is pretty trippy. But at the end of the day, this is great from a machine learning and capability perspective because this creates a data flywheel for us. Like we know where things are working, where they're not, tracking the precision recall curves to know how we should tune them to get the level of coverage that we want, but also to be economically viable. And so it's a great business model that for us incentivizes grabbing the best and greatest off-the-shelf technologies, tweaking them for our purposes, enhancing them where it makes sense, and then leveraging the incredible developments from the rest of the world to really make our entire business more efficient. And so I grabbed one example of this from our CTO, Eric, who's here in the audience, about how we've used large language models to rapidly displace what in the past would have been entire teams of machine learning engineers to quickly create these new capabilities where you just say, you can query your entire old retained data set and pull out salient information. Things like, are doors locked? Are the badge readers working? You know, is the conference room tidy? And as we do this, we already know that we can displace significant fractions of our human labor, right? And our unit economics are solid, they work today. This just makes it better, cheaper, faster for everyone involved. And so that's the exciting part for us, is how we use these to, and then it's not just on perception, but also on automating these workflows. To be able to ask the robot, you know, go check every fire extinguisher in the building, and it just gives you an automatic report. Today, these things are done, you know, fairly manually by people, but we're very quickly being able to displace that with these language models. And you can imagine where we're going, where you generate, you know, entire new 3D models at your beck and call, right? And that's the future of where this is going. And then, of course, you have this robot rolling around anyway, doing these automated patrols. So you have the ability to create real-time updated 3D maps that you can then do inference and things on later. So once you have a good driving application, it gets these incredibly sophisticated, powerful systems in human environments doing useful stuff. It's not, like I said, it's not just about the robot. It's about, you know, across this entire operating system, being able to feed in other data to make the robots useful. That's similar to like warehousing systems where it's not just how do you move from A to B, it's this giant integration to warehouse management that makes these things useful and valuable. And then, of course, I'd be remiss to say, you know, like there's obviously huge developments across things like OpenAI, multimodal models, NERFs as a good example. These things all make our lives much easier on the robot side, but also just from a business operations side. Our remote security personnel, they're often intelligence analysts. So they're writing reports, they're digging through old data. These types of large language models make that much easier for us to streamline those processes and ultimately to automate them away to where a security or a facilities program literally is running a computer program. And you can, very detailed, have a general query like keep my office safe. And it figures out exactly how to do these things. Like that's kind of where that future world is headed. It's just sort of seamless ability to make high level requests and then have the machine large language models automatically generate the detailed procedures. And so, yeah, that's Cobalt and me in a nutshell. We work in lots of different spaces, predominantly indoor, but progressing soon to outdoor. There's a whole bunch of service robots that hopefully some of you are in the audience, that run these other service robot companies that are at the application end of that spectrum versus the sort of core technology perception end of the spectrum. And so it's a entire industry that is growing up very quickly as the technology continues to mature and get cheaper. And I won't spend any time on business model things, but suffice to say that there's a lot of old legacy industries that are being rapidly impacted by automation, where it is displacing specific tasks that people have historically done to be more operationally efficient. And so it's a combination of disciplined technology development with operational moneyball in how, when, and where you deploy automation. Thank you.
Let's see, I didn't prepare any slides, so I'll just talk at you for a few minutes, and maybe I'll make my section a little bit short and dedicate that more to the Q&A side. So my name is Johnny Lee. I've been at Google for about 13 years now. Ryan is one of the folks I've worked with for a long time. I think one of the big projects I worked on that people may know about was the Tango project, which was one of the first mobile phones that had 3D sensors and 3D tracking and mapping on it. Those folks who know about SLAM and mapping probably have heard about it. And that project turned into ARCore for Google. And some of the continuations of that work include what's branded as geospatial API. I'm just curious, how many of you have used your mobile phone to do walking navigations where it puts an arrow on the ground and navigate to? Okay, so you use that here. You use sort of the remnants of the project I started. So basically, geospatial API is Google's infrastructure to basically create a SLAM map for the entire world, built off the Street View data sets. So that's really cool. Been continued to try to get them to cover indoor spaces because I definitely think there's a whole rant I have about GPS 2.0 that I could go into. I was part of the first wave of Daydream devices, and we sort of built tracking systems for headsets and VR headsets. And then there was a pivot to essentially focus on ARCore versus some of the longer-term R&D work that Tango included in it. So I decided to do a stint in robotics at Google Research, Vincent Van Hoek's group, if you're familiar with that research team, where I built a system to essentially focus on human teleoperation of robots. So we had built a program called Reach, which basically we could take a person off TaskRabbit, just a warehouse worker who knew how to use computers but weren't really tech savvy. We could sit them down with our UI. They could, within about 30 minutes, they could operate a robot at full speed. So essentially, they were faster than the robot and doing packing tasks in a warehouse environment. And we actually set up a whole production warehouse facility that was shipping product for Google. So if you ordered something from store.google.com website around 2020 to 2021, and you lived in the Bay Area, it was likely shipped with a robot. But for various sort of business reasons, that project didn't continue, and I moved back to the AR team, where I was managing a lot of the perception team for the Google's AR efforts. But I recently pivoted to start a new effort focused on all the buzzwordy things of generative AI for AR. And so there's lots of things I could talk through, like the philosophy behind some of that. I think the thing that I'm most interested in with the generative AI and AR intersection stems back from the Reach days where we're doing teleoperation, which is I really believe in human in the loop and using that as a way to bootstrap machine learning systems. And I think the RLHF work for ChatGPT, in my opinion, validated, like, yes, I believe in humans. I believe in human feedback and using technology as a way to augment human performance rather than purely replace it. So even with Reach, we were thinking about how can we take someone who's a labor worker, not a tech skilled worker, and multiply their capacity for impact by 10x. So if you can multiply physical labor productivity by 10, that would be transformative to the world. And as I was looking at the problem from a sensing, perception, machine learning problem, AR actually has a pretty strong intersection with robotics. It's all the same perception problems, but without the actuation problems. And you don't have to worry about your robots breaking in the warehouse and field, or like all the gears wearing down and all the sort of operational overhead. And you can focus on the intelligence component and basically think about humans as being able to help novice humans perform expert work through either remote assistance, which transitions well to automation and machine learning. Even in the Reach days, we talked a lot about how in the autonomous vehicle space, there's a lot of conversation around L0, L1, L2, L3, L4, L5. And we all know real autonomy takes a while and it's a long tail. And in fact, pure autonomy is potentially completely theoretical. Yet when I encountered a lot of folks in either robotics or machine learning, there's this hope to go straight to 100% autonomy and full replacement right away, which actually I just simply don't believe in. So my belief in robotics and belief in AR are all about transitioning people and improving human capability through sort of learned expertise. So happy to pontificate about that more over Q&A. So thanks.
Hey everyone, I'm Carol. Unlike the previous speakers, I don't have any background in product. I'd never done anything that made money. I'm pretty good at spending money. I'm a researcher at Google. I also spent some time at Stanford. And I wanted to share some thoughts about foundation models for robotics. So first I want to tell you, probably most of you know this, I want to tell you and briefly remind you of the bitter lesson. The bitter lesson says this: the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. The ultimate reason for this is Moore's law. So this bitter lesson was introduced by Rich Sutton. And I think this is a very insightful lesson. And if we were to break it down, it goes like this. One, we know that AI will need a lot of compute. We don't necessarily know what AI exactly will look like and how we'll achieve it, but we do know that whatever it is, it will require a lot of compute. Two, there is a trend that we can recognize, which is that computation is getting cheaper. And this trend is completely independent from AI. This is because of Moore's law, and Moore's law is happening whether we work on AI or not. So this is a very compelling trend for us to attach ourselves to. And then three, we should work on AI methods that leverage that trend. Now, it doesn't mean that we shouldn't work on algorithmic improvements to AI. It just means that we should work on such algorithms that will benefit from this trend that we recognize that is happening outside of AI. Because these are the algorithms, the methods that will eventually prevail. So now I work on robotics. So I thought, what's the equivalent of this bitter lesson in robotics? In robotics, one thing that we all really need is data. So I came up with a new bitter lesson. So let's say that the last bitter lesson was about 70 years ago. Let's say that we meet 70 years from now again here at Google. Google still exists, and I'll look a little different. And we talk about the bitter lesson that we all learned about robotics. And I think it will go like this. So one, robotics will need to understand the world through data. We don't necessarily know how robotics is solved, but we do know that we can't just enumerate all of the different cases where robots need to work, and it needs to learn it from data. Two, there is some trend. We'll talk about it in a second. We don't know what it is yet, but we're looking for a trend that is independent of robotics that we can kind of attach ourselves to and kind of ride that wave with that trend. And 3, work on robot learning methods that leverage that trend. That trend should also bring some data to robotics. All right, and eventually the methods that do leverage that trend that brings in more data to robotics, that is completely independent of robotics, will be the methods that prevail. So the only question is, what's the trend? So I guess it's fairly obvious to most people here that new trend, I suspect, will be foundation models. So if we look at the development of foundation models over the past few years, it's fairly clear that they're improving fairly, very fast. And I treat them as kind of models that are data in disguise. They look at a lot of data on the internet, and they somehow are able to bake in that data into their weights. And that allows us to then use them and leverage that data in a way that is very easy to be leveraged for robots. So let's see if they fulfill all the requirements that we had for the trend. So first, there's huge interest in foundation models outside of robotics. Foundation models will happen whether robotics cares or not. We're safe here. 2, they scale with data and compute, so they leverage the first better lesson. And 3, they're getting better at understanding the world around us. They consume more and more data, and they're better at kind of making sense of that data. So we can argue how far it's going to go and how good they are now, but I don't think we can argue that they're getting better, and they're getting increasingly better with time. So I would argue that the new better lesson will look like this. The biggest lesson that can be read from 70 years of robotics research is that general methods that leverage foundation models are ultimately the most effective. Right? So that's my hypothesis. That's the new better lesson that I want to avoid. So now we've done a little bit of work to see if we can actually show that and if that makes sense. So I wanted to share a few examples with you. So the first work where we started seeing this is this work called SACAN, where we, there should be a video here. I guess there's no video, but the basic idea of SACAN is that we can, oh, there it is. All right. Is that we can attach a large language model to a robotic system, and that allows you to talk to a robot in free natural language, and then the robot will be able to understand what you're saying, and then consider all the different skills that it knows how to do, consider the environment that it's in, and using the skills that it learned from data, it can realize what kind of plan it can carry out so that it can accomplish your command. So we go from this very intricate language where you describe very abstractly potentially what you want. For instance, you decide that I spill my Coke on the table, how would you throw it away and bring me something to help clean? You can just say, I'm thirsty, help me, or anything like that. And the robot will be able to kind of look through the library of its skills and think about how to create a plan that will accomplish that task. Now, this is how the system works, but the exciting piece about the better lesson is that we want to ride that wave of foundation models. So the most exciting piece to me is that as we started swapping out these language models to better language models, so we started with this language model called Plan, then we switched to a better language model called Palm, and also with increasing number of parameters of Palm, these are better and better language models, the robotics performance started increasing. And the reason why this is exciting to me is, usually to improve robotics performance, it either requires a ton of data or a ton of human engineering. It's really painful, and it doesn't happen just magically. And here it seems that by just swapping out one component that gets better and better over time, there's lots of people working on these things, we are getting better robotics performance kind of for free without any new robotics data. So I wanted to show you another example called inner monologue, where we kind of try to leverage this even more. So now we can consider many different models talking to each other. These are all vision language models or just language models that help the robot construct a plan, and incorporate human feedback, incorporate feedback from other models, and so on. So here the human asks, can you bring me a soda? Then a SACAN-like system creates a plan. It tells the robot, well, you should find a Coke, then pick it up. Then we have an adversarial human, happens very often, and the robot fails. But then it can ask another model, a vision language model, to ask to tell it whether it was successful or not. It tells it in natural language that it was not successful, And then it asks it another model, what is happening in the scene. That model says, I see an orange soda. Then it can ask for more clarifications to the humans. And all of these models are talking to each other via natural language. And as they're getting better, the entire system gets better. And it doesn't matter which of these systems gets better, just the entire system gets better as soon as one of those systems improves. I wanted to show you one more example. This is a model that we created, a big vision language model that takes images and text as input and outputs text. We call it PaulMe. This is a multi-model vision language model. And here we see some of the benefits of combining the data sets that we see in robotics with the large data sets that are used for these big foundation models. When we consider planning tasks for robots, when we train single specialist models, they perform at a certain level, here a little below 50%. But if we combine these data sets and throw it into the big mixture of all the data that you can find on the web and so on, the performance across all of those models gets better. So it seems that the generalist, compared on a task that the specialists were trained on, is better at those tasks, which is a very promising trend. I'll skip that. And then one more example that I wanted to show you is usually when we talk about these things, it feels fairly obvious that you can improve robot planning or this high-level decision-making by introducing vision language models or large language models, because they're kind of operate at the same level of abstraction. The question is, how can we do it so that the robot actions, the hard part of robotics, get better, right? So the piece of robotics that is hard is actually robot doing the thing, like actually getting in contact with the environment. So here's one example where this new better lesson can be shown, where rather than learning policies or writing code for a policy, we can ask a large language model to write the code for the policy for us. Now, this language model can query all kinds of perception APIs. It can write its own controllers. And it's surprisingly really, really good at that. It turns out that some of the knowledge that is in large language models, that those models already know how to do some of the low-level controls. They read robotics textbooks too. Now, the question is, how do we extract that knowledge? And we found that having them write code is actually a really good way to do that. But I think that's just one of many ways. Now, if we ask them to write the code to accomplish tasks, code is very expressive. That's how we talk to robots. That's how we program them. So you can actually do a lot of things. And with better language models, now you get better robot policies that actually interact with the world. So this is maybe another way how we can think about using foundation models to improve even the low-level robot actions and ride that wave of improvements with foundation models. And here's some examples of what this is capable of doing, and it works across many different robots, many different APIs. It can use NumPy, all kinds of different things. But overall, that's one way we can think about foundation models in robotics. How can we kind of position our field strategically so that as these models get better, our field gets better as well? And I don't think it's trivial, right? Like it might feel like we're just kind of jumping on the bandwagon, but I think it's actually quite nuanced how to do it in a way so that not only we can benefit from these foundation models, but we can also feedback and improve them as well. Thank you.
Carol's being very modest because I was at ICRA last week, and they won the best paper with this code as policy, right? So congrats. Yeah, let me go to the next slide. I'm Frank Delaert. I'm CTO at Verdant Robotics. This is a recent thing. I've been actually a professor at Georgia Tech since 2001, and I worked at Google as well. All the previous speakers have worked at Google. I worked at Google as well for 2.5 years, working on nerves mostly, while also being a professor at Georgia Tech. Worked mostly at Georgia Tech on mapping, localization, and 3D reconstruction. But when Gabe Sibley, who's in the back, who's the CEO of Verdant Robotics, pinged me on LinkedIn, like, hey, do you want to do another stint in Silicon Valley? I'm like, wow, well, probably not, but I'll talk to you. and Gabe and I are old buddies because he's also in Slam, etc. So, but then he presented this amazing vision of this company, Verdant Robotics, where we're going to, basically do something really cool at the same time, fulfill a real need of growers of our foods, for 8 billion, 9 billion people on the planet, and do that with way less chemical input. Okay, so that was a very compelling vision, and I felt, look, I can't say no. I have to join this company and help realize this vision. So that's what I did 8 months ago. Yeah, so by 2050, we will need to produce a lot more food for a lot more people. Now, the population will sort of stagnate at one point, but we're not nearly there. Okay, and we need to do this while facing a crisis of a climate crisis of crazy proportions. So something's got to give, right? And we believe that the answer is partly technological, partly taking all the things that we know from robotics and applying them in this venture of growing food for the world. This is not what the future looks like. So currently, people in organic vegetables, which is where we're trying to make our first foray, they work in 110 degrees heat. It's only going to get worse. People don't want to do it anymore. It's heartbreaking. It's literally backbreaking. Okay. So we think that robotics and AI have a better answer. So let me show you a little movie of the machine that we're building at Verdant. I hope this works. There you go. We're zooming in. So there's a tractor, and the tractor is driven by one of our personnel. We have a motto at Verdant, which is autonomy last. Okay. What is autonomous is the in this version of the machine, there is 6 spray boxes that spray weeds. So in organic chemicals, it's very expensive to weed because you can't use broad applications of pesticides. So you need to do something. You need to send in weeding crews, hand weeding crews, 12 people at a time, right? And so we're proposing a better solution. Let me see whether I can go. It's a way in, because we believe there is actually a very large future for AI in ag. So we're starting with process improvement like weeding and thinning today, but we will actually, all this data. And so here we're leaning into the bitter lesson. If we gather all that data about how vegetables grow, how climate works, etc., we can and we build methods that take advantage of that. Then we can, in 70 years, Carol will say, look, and Verdant was really on the ball there, right? So we build, we're both SLAM people, Gabe and I. So we do 3D mapping. We build models of the field. We know where every plant is. We can come back to it. We index the field, then we act in it. And currently, this is mostly weeding. So we actually spray chemical. An organic chemical derived from coconut. And that's it's very regulated, so it's a natural chemical. And then the future of Verdant is about discovering new value based on all that data that we collect while doing this weeding and thinning. The technology itself is, as I said, we just buy the tractor from Holland Case. We have an operator. We have GPS that gives us, it's RTK enabled GPS, corrected GPS. We just hang our implement, which is this large box, which 6 smaller boxes inside, and we're not going to show everything. Okay, so there might be competitors in the room, but we use a standard 3-point hitch, which is a very standard way to use implements in field. And then we have an entire sense, think, act loop times 6. We we sense the world using high definition stereo. We assign one of our sprayers, which we call Saurons, after the Eye of Sauron. We decide which sprayer will spray what weed. Hopefully we're not spraying carrots, because then the growers will be very displeased with us. And then we spray them. And at the same time, we measure how well we do. And that's basically the basis of our business plan, which can be summed up as superhuman farming. Right? In terms of R&D, we're very nose to the ground at this moment. At the moment, we want to make this work, and we're not very researchy. We're very applied. We really want to make things work, right? And this, I'm with Travis. This is basic robotics technology that we just have to make work in all corner cases. But I'll share some thoughts. LLMs and ChatGPT, I'm obsessed with them myself. When I code, which is unfortunately not every day, I love coding, but I use Copilot, and we are all using Copilot, and ChatGPT, for which we have our own private instance, which is much cheaper than every developer paying $20 a month. But I personally also implemented some things like analyzing our databases. We collect hundreds of millions of lines of logging every week, and so how to dive into that? Well, if you're an SQL wizard, you can sort of join on all these tables and all that data and analyze how well did we do, how well did that Sauron do, etc. But nobody is an SQL wizard. It's crazy, So, but ChatGPT knows it very well. So you just describe your database, and then you ask, give me an SQL query that looks at the performance of our machine in that field, with that farmer, with that crop, right? Other things that we're working on is really just, machine learning 101, efficient labeling and quality control. We have our own labeling team. We have to deal with other distribution data, like purple carrots. Carrots. The leaves of carrots are typically green and nice, etc. But when stressed, all of a sudden you can be confronted with purple leaves, and our machine learning models have never seen them. So how do you deal with that? Talking about generative models, one interesting thing that we're looking into is actually using generative models to produce much more training data than we can actually train on from real data, and maybe introduce. And so at ICRA, Ken Goldberg gave an amazing talk, and his student also won a best paper award with the Robot Garden, and they have plant simulators. Okay, so plant simulators, pretty cool, right? Nerve plants, right? Transformers are incredibly exciting, but they're also expensive. We are running with small edge NVIDIA devices. So how do you run a transformer on something that is so compute bound, okay? And that needs so much data to work well. So we would love to be able to do that. We really would love to be able to run transformers. In fact, the spatial distribution of plants and weeds and which ones to target, it's, that seems like an amazing low-hanging fruit to pluck. But we have to solve this riddle as to how do we run transformers on something that can barely run, a large YOLO model, right? So actually, I don't know whether you guys know Modeler, which is a new company by Chris Latner, but that is incredibly exciting. He might be able to speed up inference by a factor of 2, 3. Has this really cool new programming language called Mojo, which is a superset of Python. So, we're looking at all of these things. Yeah, and then I talked about generative models for synthetic images already. All right, so those are some thoughts for what we have in mind at Verdant. So thank you.
Yeah, one more speaker.
All right, last from Jim. Jim, you can take over and present. Okay, can everyone hear me?
Yes.
Okay, awesome. Okay. All right, can everyone see my screen?
Yep, we can see it.
Okay, I'll get started. Hi everyone, I am Jim, a Stanford PhD and research scientist from NVIDIA. So I'm really honored today to be among this stellar panel. And I'll switch gears a little bit from robotics and share my journey towards journalist agents in open-ended worlds. So AI agents actually have a glorious past. They have achieved really amazing milestones long before ChatGPT. For example, in 2016, DeepMind's AlphaGo beat the world champion Lee Sedol at a game of Go. And then 2 years later, AlphaZero is able to play Go and chess and shogi all at grandmaster level. And then in 2019, AI agents excelled at much more difficult real-time strategy games. Like OpenAI 5 is able to defeat the human champion at Dota, and AlphaStar dominated StarCraft. But beneath the glory, these games have one thing in common. They have a very narrowly defined goal, which is to beat the opponent. And the world is fixed and has very little room for open-ended exploration and creativity. But what we truly want are journalist agents. And I argue that they need to have the following essential properties. First, it needs to be able to pursue very complex, semantically rich, and open world objectives. Essentially, you explain what you want in an arbitrary language prompt, and the agent should perform the actions for you in a dynamic world. And second, massively multitask. A journalist agent, as its name implies, must be able to do more than just a few tasks. It should be ideally infinitely multitask, as capable as human language can express. And third, world knowledge. The agent should have a large amount of pre-trained knowledge instead of just knowing a few concepts in a limited environment. So that train of thought lands us in Minecraft, the best-selling video game of all time. And for those who are unfamiliar, Minecraft is a procedurally generated 3D voxel world. And in the game, as you can see here, you can do whatever you want. Explore the terrains, mine all kinds of materials, fight monsters, craft hundreds of tools and recipes, or build amazing structures. And it requires a very diverse range of skills to play well. So what's special about the game is that Minecraft defines no score to optimize and no fixed storyline to follow. And that makes it very well suited as a truly open-ended AI playground. And as a result, we see many humans doing super impressive things. Like here, someone built the entire Hogwarts castle, block by block, in Minecraft. And here's one more example. Someone built a functioning CPU circuit because Minecraft supports logical gates and is actually Turing complete. Here, I want to highlight a number. Minecraft has 140 million active players. And just to put this number in perspective, it is more than twice the population of UK and 5 times the number of programmers in the world. And it just so happens that gamers are, generally happier than PhDs. So they really like to stream and share. And this huge human mass produces an enormous amount of online knowledge every single day. So can we tap into this treasure trove of learning materials? And remember, data is a key ingredient in the age of foundation models. So towards these ends, we introduced MindDojo, a new open source framework to help the community develop generally capable agents using Minecraft as the kind of primordial soup. And MindDojo features 3 major parts: an open-ended environment, an internet-scale knowledge base, and journalist agents developed with the simulator and the massive data. So let's look at the first one. And here's a sample gallery of the interesting things an agent can do in MindDojo. We feature a massive benchmarking suite of more than 3,000 tasks. This is among the largest open source agent benchmark ever created to our knowledge. We implement a versatile API that unlocks the full potential of the game, such as rich input modalities, output control, and essentially the ability to customize everything. And given this simulator, we introduce around 1,500 programmatic tasks, which are tasks that have ground truth success conditions. And some examples are harvesting different resources, learn to master the technology tree, or combat various monsters. And we also introduced 1,500 creative tasks that are free-form and open-ended. And that is in contrast to the programmatic tasks, because creative tasks don't have well-defined or easily automated success criteria. For example, let's say we want the agent to build a house, but what makes a house a house? It is very difficult to use simple Python code to determine these creative missions. And the only way is to use foundation models trained on internet scale data so that the abstract concept of a house can be captured. And that motivates our second ingredient, the internet scale knowledge base part of MindDojo. So we offer 3 data sets, YouTube, Wiki, and Reddit, and combined, they are the largest open-ended agent database ever compiled. So the first is YouTube, and we find that Minecraft is among the most streamed games on YouTube, and gamers just love to talk about what they're doing. So we collected more than 700,000 videos with 2 billion words in transcript. And these transcripts would help the agent learn about human strategies and creativity without manual labeling. And second, players have compiled a large Minecraft-specific Wikipedia that explains everything you ever need to know in the game. It is just so mind-blowing. And we scraped 7,000 wiki pages with interleaving multimodal data like images, tables, and diagrams. And here are some examples. This is a gallery of all the monsters and their spawning or attack mechanisms explained. And in the wiki, it also talks about all of the hundreds, if not thousands, of crafting recipes. And finally, Minecraft subreddit is a super active forum. Players showcase their creations and also ask questions for help. So we scraped more than 300,000 posts with more than 6 million comments. And this is some example of how people use Reddit as a kind of Stack Overflow for Minecraft. And we can see that the top voted answers are actually quite good. Like here, someone is asking, why doesn't their wheat farm grow? And he also says, you need to light up the room with torches. And now, given the task suite and internet data, we have the essential components to build journalist agents. In the first MindDojo paper, we introduced a foundation model called MindClip. The idea is very simple. For our YouTube database, we have the time-aligned video clips and transcripts. And here, what you see are actually from real tutorial videos. Like here in text prompt 3, as I raise my axe in front of this pig, there's only one thing you know is going to happen. A YouTuber actually said this. And intuitively, we can train MindClip to learn the association between the video and the transcript that describes the action in the video. So MindClip outputs a score between 0 and 1. 1 means perfect description, and 0 means the text is irrelevant to the video. So this is effectively a language-prompted foundation reward model that knows the nuances of forest, animal behaviors, and even architectures in Minecraft. And then we plug in the MindClip reward function into a reinforcement learning algorithm. And this looks familiar, right? Because it's essentially RL from human feedback, or RLHF in Minecraft. And RLHF is the cornerstone algorithm that made ChatGPT possible. And I believe it will play a critical role in journalist agents as well. And here are some demos of our learned agent behavior on various tasks. So you may notice that these tasks are quite short, between 100 to 500 steps. That's because MindClip is not able to plan over very long time spans. And our hope is to build an agent that explores and makes new discoveries continuously without human intervention. And back in 2022, this goal seems quite out of reach to us. And then GPT-4K, a language model that is so good at coding and long horizon planning. So we built Voyager, the first large language model powered lifelong learning agent that plays Minecraft for hours on end. And the video here shows snippets from a single episode of Voyager, because the agent just keeps going. It's always traveling to uncharted territories, finding new things to do, picking new fights, and solving new challenges. Here, a key idea of Voyager is to use code to control an embodied agent. And GPT-4 shows a quantum leap in coding skills. So we asked it to write JavaScript code that can translate into Minecraft actions. But it isn't able to always get it right on the first try. So we developed an iterative prompting mechanism to refine the program. And there are 3 types of feedback: the execution error from the JavaScript interpreter, the environment feedback, and another GPT-4 that provides critique through self-reflection. And these help the agent refine the program effectively. And once it implements a skill correctly, we save it to a persistent skill library. So you can think of it as a code base that's authored purely by GPT-4 through trial and error. And then the agent can retrieve the skill from the library when facing similar situations in the future, so it doesn't need to write those skills again. And in this way, Voyager improves itself as it experiments more and more in Minecraft. And finally, we have yet another GPT-4 instance that proposes what tasks to do, given its own capability at the moment. And it naturally gets progressively harder over time, all without any manual prescription from us. So putting everything together, this is Voyager's no gradient architecture, where we don't train any new model or fine-tune any parameters. And this allows Voyager to self-bootstrap and explore purely in context in an open-ended world. These are the tasks that Voyager happens to pick up along the way. We didn't pre-program any of these. It's all Voyager's idea. And with some human help, as we can see in the center, it is able to do even more impressive things, like building a shelter house in a forest. I welcome you all to check out our website. This is minddojo.org. You can find our paper, videos, models, and samples from the knowledge base. MindDojo got the Best Paper Award at NeurIPS last year. And also please visit voyager.minddojo.org to check out Voyager. We open source everything, and you can start playing with it today. This is the MindDojo GitHub org. There are more exciting things coming soon, so stay tuned. And one more thing, right? If you want an excuse to play Minecraft at work, I think MindDojo is perfect for you. So lastly, I want to remind all of us, what we can do so far from MindDojo to Voyager is still far from the ingenuity that human players demonstrate, such as decorating a winter wonderland or simulating the CPU circuit. So here is a call to action for the community. If humans can do these mind-blowing tasks, then why not our AI, right? Let's find out together. And life is short. I believe we should do hardcore AI research and have fun at the same time. So please reach out to me by email or Twitter DM. And thank you so much for inviting me.
Switch to Q&A. I invite you guys to come take a seat in these hallowed chairs.
I think we'll leave this video on, right?
Yeah, do you know to switch back?
Okay.
The video can stay on, yeah.
Yeah, I think that's fine, right? So
Yeah.
people can see him when they ask him a question.
As long as you can hear us.
I think we'll have to use the microphone for him to hear us.
Cool.
Thank you guys for that. That was awesome. I appreciate you guys sharing. Cool. So we have one mic here. Do we have a mic that the question askers can use? There was a second mic. Does anyone have a mic in their hands? Sweet. All right. I'll pass this one around. Test. Cool. I'm going to kick off with one question, and then I welcome you guys to ask them. Ryan, I'm curious to ask you more questions about nerfs while you record me.
Thought I'd get a picture of you up there.
Thank you.
Nice. I appreciate it.
I think my main question has to do with like the actual ability to map anything to do with physics onto this type of stuff. Like, is there a future in which you are taking this type of incredible 3D reconstruction and then you're adding the type of context that, you know, allows robots to interact with it in a rich way? Like, is that completely sort of orthogonal to the core capabilities of nerfs, or do you view that as like that we're getting there?
There are papers that have done that. The challenge is last year there were 140 NERF papers at least 4 different conferences, and they didn't all build on each other. So they're all split. But some of them are looking at material properties. Some of them were looking at dynamics and things that move. There's articulated nerfs, deformable nerfs, animated human nerfs. There's rain and weather nerfs, but they don't all work together. And that is something I hope, if we can settle on a standard, that future papers will build to those things. I would say temporal things is one of the biggest weaknesses. So things that can be animated and moved really, really efficiently. Since no one knows about VDBs, I learned from VFX experts that they run those simulations for fire sim in some movie. If you're seeing some fire or fog or dust in the air, usually those simulations run on a CPU, and then each frame spits out one volume database for how that frame in time looked. And then it steps forward in time and spits out another one. And the renderer just goes back over each of them and renders the video very, very slowly. So solving the temporal nature to these volumes is somewhat unsolved, but I think in the next 2 years we'll see that settle.
Awesome. I'll turn it over to anyone who has a question. Just raise your hand or bring the mic.
My name is Raj. I'm the founder of HeyMoon, personal assistant. From the first 3 speakers or so, I heard the word long tail, human in the loop, edge cases being mentioned quite a bit. And one bitter lesson from my PhD was that in robotics or AI, it's very easy to get to 90% of the models, demos, use cases, but it's really the last 5 and 10%. And it was echoed by people at Google Brain and Tesla recently. Where are we with that kind of bitter lesson in robotics with LLM? Does that change?
I'm going to give the mic to Carol, because I was actually quite blown away when you published that paper where the general purpose work was really solving things more than just the domain specific work. So I think he can speak to that best.
Hi, thanks for the question. I think right now, at least my image of where the field is that we can produce specialists that can get to high 90s for very specific tasks using reinforcement learning or collecting enough data in that domain. We know how to do that. I think a few years ago, we set out the challenge to focus more on generalist agents that are maybe not extremely good at one task, but are so-so at many different tasks, or that are decent at many different tasks. And I think we're slowly getting there. And I think foundation models and things that we discussed help us get there. But I think we're still quite far from having a generalist agent that is good at all of those tasks. And actually, I don't think we have the right techniques to do that. It turns out that multitask reinforcement learning is really difficult compared to the single task case. The multitask imitation learning that works fairly well doesn't really get you to the level of performance that you need for this for these applications. So I'm not really sure how to get there, but yeah, that's like the trajectory of the field in women.
So I think it's really interesting to point out autonomous cars specifically, because the practical reality, and if you look back when Cobalt first launched, we used off-the-shelf stuff and achieved results that compared to what people do today, it's dramatically better. Like any level of analytics that you provide, any leverage factor on that human to robot ratio gives you really compelling unit economics. And then from a technical perspective, you're comparing to a human being who has 85% uptime by law, like meal periods and break periods. The standard for recording any data was maybe they wrote it on a piece of paper and shoved it in a filing cabinet. And so when you're comparing to, and then of course, like our operational environment is constrained to where you know that a robot can move around in indoor space, and you generally have good wireless connectivity, and you can use both, cellular and Wi-Fi to manage this. And so I guess I would say that it's really important as you're looking at the application specifically to find ones that, subject to where the state of the art is today and what is practically achievable, there's a whole bunch of these where it's not at all limited by the technology. It's a lot of operational lift instead. Cars are a particularly challenging one because, even for human in the loop, you don't always have good connectivity. Like you certainly, even cellular is not, it's definitely not a panacea. And like Frank, I'm sure can tell you all sorts about that from being out in fields and things where at least we have good connectivity indoors. But it's really hard because it adds operational complexity. Even looking now at outdoor operations, I think we're on the cusp of having good campus area networks to where within like say a 2-mile radius, you can have a good private LTE deployment, get good connectivity, and now you can rely on human in the loop for some applications that don't have like hard real-time constraints. But yeah, it's those sort of engineering nuances that matter as much or more than some of the technology capabilities. And then we just get to ride all of these amazing waves to make the individual systems better. The foundational models getting better makes our economics and capabilities better. And the more that we do that, the more data that we get, and it creates this flywheel. But I suspect that when you talk to, especially the super like applied application side, it's almost always these like practical nitty-gritty engineering details and not the research frameworks and yeah.
Awesome, and thanks for speaking loudly, Travis, if you're able to speak loudly.
Yeah, I could.
Hi, so my name is Adish. I was just wondering, and this is to all of you guys. So for the applied side of things, so the applied engineering and AI, I'm just wondering, are generalized models the way to go, or would it be the specialized ones? Because based off of the research that you showed, the generalized ones usually are performing better nowadays. So I'm just wondering, what are your thoughts on that, and how would you go about
I have one
addressing
thought
it?
from experience. If you saw because I had a little picture of the synthetic cats that we were training pet detection. Well, if you use Google Photos or Google image search, it has no problem detecting cats. That was like the original joke with computer vision, finding cats in YouTube videos. But the visual search service that runs behind that is so massive that when Nest wanted to put it on a little battery operated doorbell, it's not going to work. So the challenge, ties to the operating domain, which is, hey, this little battery operated device, what does it need to do? And that's where the team said, familiar faces, pets, packages, and cars. After that, we'll send the data to the cloud, and then the cloud will learn more. So you need techniques like distillation, and hopefully some better ways of taking these super foundation models and shrinking them down. In the synthetic data space, one of the interesting trends that I actually did not think would work out so well is people are taking these generative models. Let's say you want to detect packages on a doorstep, and they just type in a bunch of words into things like Midjourney and these other generators and say, packages on a doorstep, make the package broken, make the sun shining, make there be lens flare. And it just gives you all of these images that you want for your operating domain. And then you train a vision system on that. It actually works remarkably well.
Yeah, I would plus one a lot of that. Like, I think the programming of the future will basically be fine tuning. So we'll be starting with these foundation models, but you want to run in lower power and lower resources. You want to get the higher percentile on your particular domain. If you're not sort of preparing your infrastructure to fine tune large models, you should start, because I think that will be a common pattern in the future.
So I'm not an expert in large language models, but I'm a Twitter fan. So and even like people like Sam Altman have said, sometimes it's just you need an existence proof. You need a proof like, okay, this actually can work, and we're at like 1% at the moment. So I think these large language models now with transformers, with the entire world's knowledge baked into its weights, will not survive long. That's my prophecy. We will have stuff that indexes into databases, is much more efficient, and so I'm sort of optimistic. I do not want a future where we have to carry a bunch of TPUs on the back of our tractor. So instead we'll just go with a NVIDIA Orin and just better better models, and indeed fine-tuning. We don't have to carry the entire world's knowledge with those things. We just need to know. We just need the ChatGPT of ag, really, right? So I'm hopeful, and maybe some in the audience can make that next revolution. Yeah.
On that, I am wondering if it's okay to be optimistic about the availability and the affordability of the world's knowledge and the world's data, because it seems to me we've made incredible progress on effectively scraping human experience for free, and it would seem to be part of this ongoing process of making product out of it, that we're going to be putting moats around these databases, and we're going to be commercializing all the products that come out of them, and maybe the unit economics will mean that it's super affordable for people to access in the future, or to continue to update these models in the future, or maybe it's going to mean that we start to close things off. So are we going to be able to continue to develop on human experience in the future in the same way that we've done up to this point?
I say yes.
Yeah, I think it's a very philosophical question. Like, on one hand, we need core unit economics to work out to drive innovation and get systems deployed. So there's certainly a capitalist element to all of this. I think it really comes down, and I'd be really curious to poll the panelists. If you were writing an objective function for AI, what would it be to maximize the probability of a good outcome? And there's lots of things that go into that, including your personal beliefs. But like mine, for example, would be to maximize the quality of life for all humans. That would be my objective function. I think there's reasonable people who could come up with very different objective functions, and I think that they all could have merits. But I think that one, on the whole, for the people I know, care about, myself, and humanity, I think is a pretty good one. Yeah, so I don't know. I think the objective function matters a lot. Like, I'd rather that than build paper clips, for example.
I do think there's a big disconnect between these language models that operate on digital information that's pretty close to the way it exists in the world. So they'll operate on a chat thread, a web page, a document. That is the asset. The asset is digital, so it's learning about digital assets. With robots that need to learn to work in the real world, that's where we do have a data sparsity problem, that there is not massive open data sets of 3D volumetric data. And Johnny mentioned, we always wanted Project Tango to work in your house, to map your house. And I guess we could say the reason it doesn't is lawyers, not technology. So, Google's VPS works on Street View data from outdoors, and your phone can work outdoors, but the reason it doesn't work in your house is because not a lot of people want to collect all that private data in your house. And even if they did, it would still be kept private. So how do you, Doug's here, Doug worked on Amazon Astro, which had to work, it was a mobile robot that has to work in your home. I have to imagine that was a massive data challenge of where do you go get all that data of people's homes? I think you guys were like renting Airbnbs and things like that. So to Andrea's question, I think we're going to do amazing things with language, but the spatial AIs, I think, will be starved for a little bit until we figure out the data challenge.
I can go next. So I had a question, actually pretty similar to someone already asked. So it's a bit of answer already, but maybe a spicier question. So with ChatGPT and large language models, we've seen I'm a product leader at Scale, Scale AI. We've seen whole NLP ML teams upended or displaced because a PM or a software engineer can just do basic NLP using a prompt now. And so with maybe in the future PAMI, but also right now there's Segment Anything. There's RAM, which was Oppo came out with recently. These foundational perception models are coming out. So I'm curious, for the research and the industry perspective, what perception planning teams can do now to prepare for this like future where anyone can segment anything?
I'll pass it back that way, but I think like fine-tuning large models, maybe that sounds repetitive, but like there's still an enormous if your entire product can be satisfied with an off-the-shelf model, yeah, you're probably in a bit of a dangerous position. But I would say there's probably a minority of folks because these large language models and multimodal models as they come out are only based on the training set they had available. And so they're going to be going after the largest swath of things online. And so like my particular interest, as Ryan was talking about, is like data from the real world is still, even product imagery on the shelves, e-commerce imagery doesn't look the same as things look like in their store. And so there's an enormous gap that you can build and develop specialization in that the base models won't have. And so plenty of space there, in my opinion. Oh, by the way, I want to say like Voyager is one of the coolest things I had seen recently and told everyone about it when I saw it. I basically want to build Voyager, but for real people. So I really like the work, Jim.
I love to chat. Yeah.
I think we have time for one or two more, and then we can all.
I would just weigh in on the
last
core
one.
to that, though, is like there's really three things that you have to decide. Like, where are you innovating? Are you innovating on the model, the bridging from digital to physical and back, or on unique data sets? And those become like, you're probably one, maybe two of those. But you should just know like what is the core to what you're trying to build. And
But I think, Travis, what you're showing is it's not only about the technology, but about the execution and the operations and getting it in the hands of customers and building the business model, and that won't go away. So I don't think you will sort of out LLM yourself there. So
I would maybe just comment on perception aspects. So what we've seen with LLMs is pretty incredible, and they clearly have these emergent properties that happen at certain scales. And I think at least my mind immediately goes towards these vision language models will go exact same way at certain size that these properties will emerge. They'll just understand all the visual world all at once, and they'll be as powerful as LLMs. I think so far that hasn't been true. Even though we've been trying to scale these models and
we have 70 years.
That's right. So
we just need another 3 and it'll be true.
Yeah. But like a more pessimistic view at what is happening now is, even though we've been trying really, really hard, we haven't seen these emergent properties for vision. We've been scaling up these models. There's lots of models that are scaled up right now, and they don't seem to show the same properties that we have seen with LLMs. Now we're starting to combine the two and kind of hope for some of these properties to transfer from language to visions, but we haven't seen them. So just wanted to put that out there as well.
Hi, I'm Saksham. I'm a graduate from Stanford. I really enjoyed the talk so far, and throughout the talk, I heard terms like LLMs and transformers being brought about. I had a question about what's your thought about diffusion policies and what's their role in robotics? Do you think that diffusion would be something that would play like an integral role in robotics, or something that's like a small key set that was there in 2022?
I'm happy to pontificate if there's not too many. Obviously diffusion for synthetic data was brought up several times, so that's really good. Something that I haven't seen as much, I'd love to see, is diffusion motion and diffusion trajectories and things like that. So like large data sets of watching people or watching equipment even, can you synthesize accurate or efficient motion from that? And that there's such a dearth of that in there that I wish there was more.
Actually, on that, one of the things you might do if you're making IoT computer vision devices is something like maybe fitness at home. There's apps doing that. I think Peloton has tried to introduce computer vision. So let's say you want to have a camera that's in a home counting people doing sit-ups or push-ups or helping people with fitness. where will you get that data? And you go, oh, I'll crawl YouTube and I'll train on YouTube data. But do you know what YouTube data looks like? Beautiful people in very tight clothes, very well lit, with no occlusions between the camera and them. It's not what happens when you give people a camera and they point it at themselves in their robe, in a dark room, lit by the television, with their dog in the way. And so even if we want to generate that data, we still have this problem of where do we get it from? And so there is this dearth of that.
So there are some examples of diffusion policies. There was a wonderful paper from Shuran Song's group from NYU, from Columbia, sorry, that introduces it, and they show some really incredible results. That's for using it for robotic control. I think there are some examples of generating motions and trajectories with diffusion models as well.
Shuran's cool.
Yeah. So check out her work for sure. Yeah, I think right now we have these two very powerful model classes, diffusion for image generation and transformers for basically everything else. We have been trying generating images with transformers, and so far it hasn't matched diffusion performance. There is lots of pros and cons between the two. One problem with using diffusion policies for robotics is that they're fairly slow, and it takes quite a few refinement steps to get to the action that you actually need. Now, that gets you maybe to a very, very good action. You can generate that action very precisely, but maybe that doesn't matter as much as speed, for instance. But yeah, there's lots of pros and cons. I think that's a longer conversation, maybe.
Awesome. Our last guest. All right, guys. So Jim and Carol, I was kind of struck by the way you're using parse model. And then from the programs out, and that goes to the robot or it goes to the simulator, and maybe an HR loop in there. It's like it's English all over the place. And I'm kind of wondering, is English the API in all of these systems, or is there a different API? Vector space, data space, but it's really the marketplace system, which is the API.
Jim, I'm curious what you have to say, but maybe just to comment.
I don't know if the microphone is working. So
Sorry, I cannot hear very clearly the question.
I can repeat the question for you.
Please.
Can you hear me okay?
Yes, you are.
It was off. Yeah, the question was that in our works we're using English as this universal API because we are using language models. Is English the right API, or should it be some kind of embedding space or something like that? Is that accurate? Yeah, so a few thoughts there, maybe slightly disconnected. On one side, I feel like large language models actually just happen to be trained on language, and that's maybe a controversial take, that they don't have that much to do with language. To me, they seem more like a universal computer or a pattern recognizer, and we've seen a lot of works showcasing that. Even things such as Palmy, where you can just like plug in something that tokenizes images, puts them into some kind of embedding, and then the language models can quickly understand how to deal with them. So it's more a way of having this universal computer that takes some tokens and outputs some other tokens. Now, it happens to be trained on language because we have a lot of it, and we have a lot of very interesting data in language with code and all kinds of different logical kind of tasks. So that's where these properties emerge. But my belief is that they just happen to be trained on language, but they're not necessarily core language, machineries. Now, in terms of whether we should be using English or not, the one kind of thought I had once we started using them is that language is really wonderful. It's an API that we all agree on without ever talking to different research groups and so on. Kind of every research that is happening right now is using language. And that's a really great universal API. It's at the right level of abstractions many times. So we've been working on all kinds of different multitask algorithms where we want to discover some kind of embedding space of the skills you have. But if you keep on scaling this up and you introduce multi-agent interactions and so on, eventually you will arrive at language. That's how language came about. So I feel like it is a wonderful API. It's fairly expressive. I'm not sure whether it will take us all the way, especially for low-level control, where some of the things I can't describe with language, but I know how to do them. But I guess we'll have to see.
I think
let Jim speak,
Carol.
right?
Oh, sorry. Yeah.
No, go
I
ahead.
think Carol. Thanks. Okay. So I think Carol covered the multimodal part really well, and I agree with all of what he just said. I want to dive a little bit deeper into a very special modality in language, and that is coding. I think coding just holds a super special status here, because from a learning perspective, coding is a highly structured space, and it helps reasoning. And actually, there are papers showing that the better you do on coding, the more reasoning power the LLM has. And in fact, if I recall correctly, I believe ChatGPT was fine-tuned not from GPT-3, but from Codex. So Codex was ChatGPT's base model. And then they build like dialogue and everything on top. So that's why ChatGPT and later GPT-4 has a super strong reasoning ability. And that is one of the key distinguishing factor from all of the open source models out there. Like Llama has way worse coding and reasoning abilities. So there's that from learning perspective. And the second is from a control perspective. So I think I see coding as the arm and leg for LLMs. It is the actuator interface into the digital or even the physical world, right? Like Voyager is using coding to give it the arms and legs of a Minecraft agent inside the simulated open-ended world. And then Carol's group, they code as policy, giving LLM kind of a control of a robot API. So code is the way for LLM to interact with the rest of the world, including using tools or just controlling embodied agents. And third, from a more kind of future, like sci-fi-ish perspective, I believe coding is the way to make large language models self-hosting. So essentially, if you like, what is Transformer, right? It's a bunch of Python code. It's a bunch of CUDA code. And I believe LLMs may someday improve themselves by just rewriting their own code. And I'm actually pretty confident OpenAI is doing that already, because GPT-4 just shows phenomenal coding abilities. And it would be just dumb not to use this to help the development of GPT-5. And at some point, it's going to be completely autonomous. So coding holds a very special place there.
Can I just add one more thing? It's like, you guys have seen the movie Her, right? And at the end, humans are just too slow. So I think, sorry, Gabe, but I think language is a transient. We're just a transient on the way to something much more, something much faster. In fact, there is already people, with the limited context length of ChatGPT. Sometimes I even reach the 8,000, token length. I'm like, okay. And the API complains. And so people have said, hey, ChatGPT, why don't you summarize everything that we said before, but you can use any tokens it wants. And it produces this unrecognizable gobbledygook, right? With lots of emojis and Unicodes. And we can't understand it, but the language models can. So think about that. All right. Yeah.
Just two things to add on that. That was amazing when I saw that it came up with its own language and it could read it back. I think that was the key. It knew what it meant. There is a code of language. I'm the son of a lawyer, and I think we don't use legalese enough. In fact, growing up with a lawyer, my agreement to do my chores included, I shall mow the lawn every fortnight, notwithstanding the foregoing and some bullshit. Yes. And I would ask my dad, I was like, why do you write like this? Because he would come home and talk like that. And he goes, legalese exists so there's no ambiguity. And I think that's somewhat missing from language models and especially robot interfaces. I do think really smart agents will at least be able to, if you said something that could be interpreted different ways, ask you back before the robot goes and does something really bad. I think that would be good. but we may find more ways to speak more clearly. I have one plug related to all of this sensing, though. I'm just showing a graphic here for a book called An Immense World. This came out, I don't know, maybe in the past 6 months. And I'm listening to the audiobook. It's by this guy, Ed Young, and he narrates it himself. It's fantastic. It is about animals, from insects to mammals, and how they sense and how they communicate. And having worked with or being around robotics folks for the past decade, every single chapter, I'm like, why do we keep putting 4K cameras on robots? There's like way better sensors to do these things. I would encourage, there should be 50 sales of this book out there. And you will be thinking, oh, I should sense that way. I should communicate that way. I don't have to always have just speakers and 4K cameras and LiDARs. There's way better ways we can communicate with the world. And animals have shown us that, and we haven't copied it enough. It's called An Immense World by Ed Young.
With that, another round of applause for our panelists.
Thank you. Appreciate it. We are at the end of our presentation. I do have a challenge for you all. We have a lot of drinks in that space. Feel free to grab one final drink before you leave, but thank you again for joining us. And thank you, Josh from Innovation Endeavor, for putting this event together. Thank you.
Thanks everyone. Thanks for having me.
Programming themselves, something very similar to